Thank you very much. So I'm going to continue what Ulrike has started. She told you about what happens to the baryons along the cosmic web when they plunge in massive filament, in massive halos. So we are going to probe deeper and go past the virial shock inside the virial radius of massive halos, to see if we still have a connection between the cosmic web in terms of the baryon and the galaxies in the midst of this dense environment. So as you know, in a standard view of cold gas accretion into galaxies, this might not necessarily be the case, because for halos above 10 to the 12 solar masses, we tend to think that a cold filamentary accretion, so-called cold flows with a telltale helicoidal structure, might not actually happen. They are expected to get heat shocked at entry into the halos. And so you have a binary view with low mass halos having this nice cold flows, this nice connection to the cosmic web, and these being maybe mostly lost as you go to higher mass. But this might not necessarily be the case, because in between cold and hot accretion, it's work mostly by Avishai and collaborators, you can also have so-called cold and hot accretion, multi-phase accretion. So some cold gas can possibly breach into the halos anyway, and what happens to this gas once it's into a massive halos is really model dependent. But just to give a really brief recap, depending on whether you consider the impacts of several things, for instance, inhomogeneities in your stream or expansion of the stream past the shock, you can get a very different range, when you get multi-phase accretion. And for instance, in this work by Nicolas Cornwell from 2018, his model finds multi-phase accretion all the way to cluster scales below redshift 2, provided that the filament is contrasted enough. So it's really not guaranteed that we can have no cold gas at all within massive halos. And maybe we should rejoice at that, because actually it's no secret in observations of clusters that we do see a lot of cold gas within clusters. There are different ways to measure that through H1 measurements, for instance, in the Virgo cluster, or a popular method is looking at the magnesium-2 absorbers. Many studies actually find large amount of cold gas far away from the central galaxies, hundreds of kiloparsec away from central galaxies. So not typically associated with outflows. And in this recent work, for instance, they go even further and show that the location of these magnesium-2 absorbers is actually correlated to the position of the satellite galaxies in the cluster. So this is what you're seeing here. This is the PDF of the mean distance between magnesium-2 absorbers and their nearest satellite galaxies. The orange curve is what you expect for MG2 absorber being resampled. So this is the null hypothesis, if you will. If there is no signal, you can see that you would expect absorbers in galaxies to be at about 400 kiloparsec from each other on average. And if you look at what really happens in cluster, they're actually much closer to each other. So this cold gas is actually quite strikingly associated with satellites. And in observations, there are different explanations for this. Some suggest it's actually being stripped from infilling satellites. And in these papers, I also suggest maybe the presence of the inflow, and I think this is the first paper that suggests this. And what they did to suggest that is that they looked at the difference in velocity between the magnesium-2 absorbers and the brightest cluster galaxy. And if you look at weak magnesium-2 absorbers, this is the purple line. The statistics is not great, but they start to see a double peak at negative velocities. So it is weak evidence at this point, but you might have what resemble an inflow of somewhat cool gas within massive clusters. So you might be able to maintain this connection between the baryonic cosmic web and the galaxies deep into the cluster through these processes. And before I go a bit deeper in that, I'd like to also highlight something, is that there is a very clear smoking gun of that we see in simulation that is easily testable in observation, is that if you look at the distribution of satellites in these massive halos at a relatively low redshift, and you can very clearly see that it tends to recapitulate the structure of the cold flows, and that's what I'm going to try to convince you of. So this is what this is showing. So let's say we have a central galaxy and we have a massive halos it is embedded in. And what I did is that I looked at two different angles. This is the angle between the position of a satellite and the minor axis of the central galaxy. And this is the angle between the position of the satellites and the filament. And we do that in different radial shells from the center of the halo. So in green, you are in the center. In red, you are far away from the center. And what you see here is that if you look at alignment with the filament, as you would expect, far away from the center, you really see a peak of the cosine in 1 and a depletion in 0, characteristic of the fact that the satellites are falling along the filament. Nothing weird here, and it progressively decreases as you go inside the halos. And while this trend decreases, you see the alignment in the galactic plane, so orthogonal to the minor axis. You see this alignment increase, and this is what this peak is showing you here. So you really have a balance between first coming with the filament and then realigning with the galaxies, the central galaxy. And of course, these two, the filament and the plane, for massive galaxies, are correlated. We usually attribute that to spin flips due to mergers. So of course, in practice, on the full population, the connection with the cosmic web never actually disappears. But the fact that it's actually a transition can be best seen if you select only this subpopulation of central galaxies that have a plane fairly orthogonal to the filament. So you really select the population of galaxies where aligning with the galactic plane or aligning with the filament are competitive effects, so that you can see whether the competition is actually happening. And what you see here now very clearly is that this is a striking transition. Here we're looking at alignment with the filament. Peak in 1 is indicative of alignment. So far away from the center, you're very aligned. And you progressively lose that trend with the filament as you go deeper and deeper into the cluster. And as you lose this trend, you progressively realign with the galactic plane. So here, I think the fact that it's a transition is pretty striking, and this is not just a geometrical spatial transition. You can see also that those inner satellites, they actually align their orbit with the spin of the central galaxies. If you look at the orbital momentum of these satellites, you can look at the angle between the orbital momentum of the satellite and the spin of the central galaxy. And you can see that far away from the center in red, there's not much correlation. And as you go deeper into the cluster, the orbital momentum of the satellite and the spin of the central tend to realign. So you really have a structure that's extremely similar to what you see for cold flows, with this Zin stream falling from filaments and then realigning with the plane of the central. And by the way, this effect is of course, much stronger if your central is a very nice disk. So here, going from orange to yellow, you get things that are more and more disky. And in that direction, this quantifies the strength of the alignment signal. And you can see that at whole halo mass, the diskier the central, the stronger this effect actually is. So it does suggest that maybe this is a smoking gun for a cold infill, and that the satellites get dragged inside these massive halos with the inflows in ways that are still visible at redshift 0, basically. But please bear in mind that, once again, in practice, stochastically, some major mergers and some strong minor mergers are still going to realign this plane, the plane of the galaxy, with the filament. And so this transition from filament to the galaxies is not always a competition. For very massive galaxies, these effects tend to be highly correlated. So you never lose the connection with the cosmic web. And in clusters where centrals are tend to be extremely massive and have a spin extremely orthogonal to the filament, these effects aligning with the plane of the filament actually reinforce each other. All right, so we have this nice smoking gun. So to go a bit further, I want to now focus specifically on filaments inside clusters. And something I was interested in seeing was whether the presence of somewhat cold gas along filaments in cluster could have an effect on the fate of galaxies in clusters, in particular on the quenching, right? Whether galaxies could be could retain more of their gas and keep forming stars longer because they are falling along these streams. And to do this, I worked with a student, Sachin Kotesha, and used the 300 that I don't need to present anymore, 300 the 24 simulated clusters, and reconstructed the filaments with disperse. We are talking about the gas filaments in that case. And the first thing we were wondering is whether these filaments actually make sense. Are they just slightly over dense regions, or do we have other properties, specific properties for the gas? And so with two students, we first confirmed that these are actually regions of reduced gas temperature. So here we present the profile of the temperature with respect to this quantity, distance to filament versus distance to the center, which is basically an angular separation. And the reason why you need to use an angular separation is because these two distances are not orthogonal, they're not independent measurements. So if you just look at the distance to filament, you're really biased toward the center of the cluster. So we can just look at one curve, the red curve, which is what happened within the virial radius. And you can see that as you reduce the angular separation to the filament, you still see a pretty sizable dip in temperature. So bear in mind that the 300 is a very intermediate resolution simulation, so I'm not at liberty to discuss exactly what happens to this gas more than that. But we do see deep into the cluster the trace of a cooler inflow into the clusters. And when I say inflow, I do mean inflow. Well, what we also checked is that these intra-cluster filaments actually host streams that are more coherent than the rest of the cluster. And one way to show that, for instance, is just to look at the velocity of the gas particles in that case, and look at the angle between the velocity of the gas and the nearest filaments. And let's look at this quantity as a function of angular separation again. The dashed line is what you expect if you have no enhancement in filaments. So this is purely radial flows in a sense. And the solid line is what we actually see. So you can really see that at the spine of the filament, you have a strong alignment between the velocity of the gas and the filament. So the diffuse gas markedly flows inward along the filament, even in clusters. And this is not just the gas, by the way. This is also the galaxies. So we have this picture where we have these regions that are a bit cooler than the rest of the intracluster medium, and where gas and galaxies are flowing together. And of course, the first thing you can test is that maybe it should impact quenching. If you are falling within some cold gas, maybe you can have more accretion deeper into the halo. maybe less random pressure stripping, maybe star formation. So I don't have time to go one by one into all these aspects. So I'll just show you the results for the gas fraction, the cold gas fraction within halos. And for this study, we're going to study 3 bins of angular separation. The reason for these bins are that they are pretty useful to wash out the effect of backsplash galaxies. If you look at this bin, the fraction of backsplash is going to be similar within the bin. So if you look with at only 13-fold galaxy and then backsplashes, you get the same result. So let's look at how this fraction of cold gas evolves for galaxies outside the cluster and for galaxies in the cluster. So outside the cluster, no surprise, we find the results that at this stage also has some observational confirmation that as you go closer to the filament, so that's for going from green to blue, you get less cold gas, so you get some amount of pre-processing, and I think we will hear more about that today. But strikingly, when you go inside the cluster, the exact opposite happens. Now, getting closer to the filaments, green to blue again, helps you retain more gas than being here somewhere else in the ICM. And so you clearly see an effect of this very specific dynamics of the gas within the filament inside cluster that helps galaxies preserve their accretion. And really the difference between here and here is that here you're going from underdense to a very dense region. Here, everywhere, the entire medium is dense and turbulent. So what really matters is having some area where gas can be cooler. And this is observed at all stellar mass, at all halo mass. Here, this is only for galaxies outside of groups, because that's a big issue, as Ulrike discussed. But we actually see the same effect within groups. And there are many effects at play in this. The only one I will discuss is the fact that cold gas accretion is actually preserved in this region, and that was of the reason why those galaxies keep getting more gas. So here's the fraction of accreting halos for different angular separation, and we see once again this dichotomy where outside the cluster you get less cold accretion near filament, and inside the cluster you get more. Okay, so yeah, this is just an example. You can also look at dynamic properties, and it's also interesting, but I don't have too much time to go into that. So I will just leave you with this message that even deep in clusters, we can find some trace of not cold flows, but cooler gas accretion that helps at least satellites in their midst preserve accretion and the ability to form stars. Yeah, so I will stop here.
Thank you. Excellent. Any questions? Sukyan.
First, congratulations to those who have completed the project 300. I think it's a really wonderful project, and after such a big effort, team effort. Regarding your probably previous slide, yeah, that's right. So my question is, what is the temporal resolution of 300? Because you have shown us that environmental effect must be working in progress on the galaxies, satellite galaxies and clusters, but can you actually see how gas is affected by the environmental effect, snapshot by snapshot?
So you can technically, so very intermediate resolutions. So when we are comparing different snapshots, we're talking almost 100 mega a year here. So we're not really doing this this way when we want to see the gas being stripped. So something we did to see whether the gas was being stripped or not was trying to define parameters that we could look at in one single snapshot to estimate this. And for instance, we define this parameter, which basically, if you look at the galaxy in phase space, three components: dark matter, stars, and gas. One thing we define is the difference between the velocity of the gas and the velocity of the stars and dark matter, and normalized by the dispersion of the stars. And what this parameter tells you is whether you're in that situation of a normal gas-rich galaxies with a small parameter, or whether you're starting to undergo stripping, where the gas is kinematically disconnected from the stars. And at the other extreme, you get this case where this gas is not actually associated with the galaxy. It's a resolution effect. It's actually the ICM. So when you look at this parameter, you get an idea of how dynamically disturbed the galaxy is without having to look at snapshot after snapshot. And what we find is exactly the same thing. This is the result inside the cluster. As you go towards the spine of the filament, you decrease this parameter, which means the gas remains more and more bound and kinematically coherent with the stars and dark matter.
Thank you.
If I may just add to that, so the 300 are constantly reinventing themselves. It's not finished. So there are newer high resolution runs. There are also towards smaller, lower mass clusters now. There are multiple semi-analytic models, and there was a paper that did look at quenching and using the SAMs, so the gas removal in those. But Charlotte says correctly that this work, and also what I showed, was based on the older runs that are not lending themselves so well to this kind of investigation.
I just wanted to, can you go back to the cos alpha, cos beta, the realignment thing? I'm just a bit, at the beginning of the presentation. Yeah. So my question is that there's two effects happening at the same time. One of them being that the filament may move a little bit. The spin of the galaxy may move a little bit with time as well. So what you're seeing here when you compare the different color line is not only the fact that there is indeed some realignment because of torquing or whatever, but that also that the thing you're comparing to is also moving with time. So how can you correct with that?
When I say, that's why I say my interpretation of that is that this is a smoking gun of the satellite being dragged into filaments. I'm not saying that individual satellites realign. I'm saying when you see the full distribution of satellites, you see the inner satellites being aligned differently than the one outside. And for me, this is more a sign of the filament not being, well, the filament they came in not being oriented the same way, because the other one were accreted later in time. So yeah, it's not, I'm not talking about a dynamical effect necessarily of one filament realigning. This is a improper way of saying this.
But I mean, in principle, it's doable, right?
It could be also, but this is in Horizon AGN where the disks are not really disks, so at depth they can tidally impact the satellites so far away to actually realign them individually.
Thank you for that great talk. I'm interested in the net effect of intercluster filaments on quenching. So were you saying that star formation is actually increased by intercluster filaments, or is it just that it's like
preserved? It's preserved. I'd say that the quenching is delayed, because if you look at, let's say, just this, the gas fraction, there's something that's still really clear, is that if you want to have a lot of cold gas, it's still better to be outside the cluster than inside, right? Even if you're along a filament. Yeah. So we're not talking about enhancing star formation here. We're really talking about decreased or delayed quenching.
Oh, thank you.
Just
a quick question. You spoke during your talk about the filament. I guess in clusters it's typically more than one. So what do you mean by the filament here?
Oh, well, it's not just one filament. We look around. We have in practice 5 to 6 filaments around.
So it's the average over.
Yeah. It's stacked along each filament direction.
And compared to the measurements we did almost 10 years ago now, in the correlation you're finding seem to be quite stronger. Why is that? Is it to do with better resolution, or
the correlation
between orientation? I mean, the signal you get of the order of 50% or more in the orientation, no?
So you're talking about orientation. So you're talking about the satellites.
But if you can show the slide that Corentin referred to.
Okay.
Like here it's 1.8 or 1.4. This is quite strong.
Yeah, well, it's not spin alignment, right? It's alignment along the filament, and it's in rather massive galaxies. So I don't know if it's that striking. It's definitely what we see in the 300, and that was also very much visible on Ulrike's slides, that you really have a tendency of the satellites to be along the filament. This is what this means. This means that satellites are infalling along filaments. And yes, we're focusing here on massive galaxies in rather big halos with a lot of satellites. In terms of average angle, this is strong. This is strong, but still, you still have a lot of spread. It's not perfectly aligned.
Other questions? I wondered if you're looking at any similar questions at higher redshift, like 2 or 3, or if anybody is with the 300, if they can.
So yeah, I'm very interested in that. I have started a little bit, and it's interesting because at high redshift you can also have actually enhanced star formation, especially on the leading edge of the galaxy falling in. So there are also other effects that appear, but yeah, it's very much work in progress.
So maybe the next speaker can set up, and we could take one more quick question during that time. Corentin.
If you do the same job as these two plots, but instead of looking at satellites, you look at gas, and do you get the same signal in terms of the realignments? So in other terms, it's like are the satellites realigning in the same way as the gas is realigning?
So that's the part I haven't done in Horizon AGN. I have only looked at the gas in the big 300 clusters, which in that sense is in the easier case, because you very rarely have a nice galactic disk orthogonal to the filaments around. And even if it's orthogonal to one filament, there are many filaments anyway. So that's not something I have looked at in Horizon AGN, so I can't really tell.
Okay, super. So let's thank Charlotte again.